Alright, so next we'll look at non-rigid transformations. So basically, now we're going to take the graph and modify its shape by stretching it either vertically like that or horizontally like that. So let's see when does that happen. So if you have your function f of x and you want to graph like 2 times f of x, or you want to graph a third f of x, how is that graph or this graph compared to the graph of f of x? So basically, if you're multiplying the whole function by a constant, and that constant can either be a number between 0 and 1, like a third, or a number greater than 1, we're going to have either a vertical shrink or a vertical stretch. So let's see. Okay. When you have a constant c greater than 1, so if you have like 2 times f of x, your original graph is this blue one. So this is f of x, and you want to graph, let's say, 2 times f of x. 2 times f of x is going to stretch the graph. So you take this blue graph and you just stretch it vertically. So I'm not taking the graph and stretching it horizontally. I'm taking the graph, so if it was like a wired or an elastic, well, and I stretch it. Okay, so if I have a point xy on my initial graph, then on the other graph, this point is going to turn into x and c times y. If I'm doing 2 times f of x, the y coordinate gets multiplied by that constant c, be it 2 or 5 or 6. Okay, so when we're multiplying the graph by a constant greater than 1, we have a vertical stretch. And this is what happens. Now, if the constant that you're multiplying the graph is between 0 and 1, so if it's like a third times f of x, so now your f of x, the blue one, is this one, then a third times f of x, the red one, I'm compressing the graph. I'm taking f of x and I'm compressing it, or I'm shrinking it by that much. So when the constant between 0 and 1, we have a vertical shrink. So a point xy on the graph is still going to turn into a point xc times y, but keep in mind that c is a fraction. It's something between 0 and 1, so the y gets smaller. You're multiplying the y by a 1/2, 1/3, 2/3, 3/4. So the y gets smaller. The y gets multiplied by c. So let's look at an example. So if I have, again, f of x equals x squared, and I want 3x squared, okay? So I'm in the case where c is greater than 1. So what's going to happen? We're going to have a vertical stretch. So let's follow a point. Let's take a point 1, 1 right here. 1, 1 on the x squared. Where is that point going to go? So imagine taking this point. So I have a vertical stretch. So I'm stretching this because I want to get 3x squared, right? So I'm stretching this by a factor of 3. So this point is going to get stretched to here. So this point 1, 1 becomes 1, 3. I multiplied the y value by 3. So I'm taking this and I stretched it. So stretching it, it pulls it away from the x-axis. So the point 1, 1 became 1, 3. What if I want to shrink it? So now if I want to graph f of x 1/4 x squared, well, then c is 1/4 in this case, and it's a constant between 0 and 1. So I'm going to shrink the graph of f of x. So I'm going to take the graph of f of x and shrink it. I'm going to put it in towards the x-axis. So the point 1, 1 is going to go to the point right here, 1, and I multiply the y coordinate by 1/4, so 1 and 1/4, which looks like 1/4 right here, right? So shrinking the graph, I shrank it, pulls it away towards the x-axis. So the thing we need, so you see how the shape of the graph changed? Like this piece right here is the same as this piece right here stretched. So the graphs are not the same. They're stretched or they are compressed, shrunk. So this piece got stretched like this, or it got shrunk, compressed like this. So this is the first example of a non-rigid transformation. So we can take the graph that we have and we can either stretch it vertically, or we can take the graph that we have and we compress it. So, well, we can do exactly the same thing but horizontally now. So I'm going to take my graph. Now I'm going to take my graph f of x and I'm either going to compress it horizontally. So I'm going to take it and compress it horizontally. So like an accordion. Boop, I compressed it like this way. Or I take it, my graph, and I stretch it horizontally this way, like the accordion going this way. So the horizontal stretch and shrink happens when the constant is with the variable x, because notice when we have a horizontal shrink, the x changed. The x was here and then it went here. The x was here and then it went there. Opposed to vertically, where the y changed. It was here and then it went there. Okay, so let's see in this case. So if c is greater than 1, so think about it. I have, this is my f of x, right here, f of x. And then the red one is f of 2x, for example. Cx. So if 2 is greater than 1, so if the constant is greater than 1, the constant that x is multiplied by, then I am dealing with a shrink. I took the blue graph, the original graph of f of x, and I shrunk it horizontally to get the graph of f of 2 of x. So this is what happens. And a point right here, x, y, well, where did it go? Well, I know that the y coordinate didn't change. It just went here, right? It went here. What is the coordinate of that point? Well, the x changed. The x, in this case, was divided by c, and the y stayed the same. So point xy on the original graph became x divided by c, and the y stayed the same. Now, if the constant is between 0 and 1, so if I have f of x, and then I want the graph of f of, I don't know, let's say 1/3 x. So the c, the x is multiplied by 1/3. Then the graph is going to be horizontally stretched. So it's here and it goes there. So a point xy on the original graph became, well, the y stayed the same. and the x got divided by c. But notice the x is right here for the blue one, and the x is right here for the other one. Why is that? Well, when you divide by a third, if c is a third, when you divide by a third, it's the same as multiplying by 3. Because x divided by c, if c in my case is a third, then when I rewrite this as not superfraction, now I'll get 3 over 3x. So x was here, and then it went to 3x. So let's look at an example. I have my regular function, absolute value. And if I want to find the graph of absolute value of 2x, so c is 2, c is 2 is greater than 1. So what am I going to do? I'm going to shrink horizontally. So I'm going to take the graph of this one and I'm going to shrink it horizontally. So let's take a point. Again, let's take the point 2, 2, for example. So the point 2, 2 on the graph of f of x, if I shrink it, when I shrink the point, the y is going to stay the same, right? The point is going to go to right here, and this point, the y is the same, and the x was divided by that factor c. So the x is 2 divided by 2 because c is 2 in this case. So the point 2, 2 went to the point 1, 2. Because, so this portion of the graph got shrunk horizontally. This portion of the graph got shrunk and now it became this portion, green one. Similarly, if c is a third, so in this case, I can rewrite this as 1/3 times x, which means that this is my c. So if c is a constant between 0 and 1, I'm dealing with the stretch, a horizontal stretch. So that means that I'm going to take this original function, square root of x, and I'm going to stretch it horizontally by a factor of 1/3. So the y is going to stay the same, it's just the x is going to be divided by c. So the point 2, 2, I'm going to write it right here. The point 2, 2, when I do a horizontal stretch by 1/3, so c is 1/3, is going to turn into the point 2 divided by c, but c is 1/3, and the y stays the same. So 2 divided by 1/3 is 6, and the y was 2. 6 and 2. So the point 2, 2 became almost 6, 2. So I took this and I stretched it horizontally. The point 2, 2 became the point 6, 2. Okay, I know this is a lot of new information and there are a lot of rules, C, horizontal, vertical, and all that stuff, but let's put it all together and hopefully you can refer to this sheet when you're trying to solve problems. So the main thing that to make your life easier, you should do the transformation in this order. So transformations can be combined within the same function, so that one graph can be shifted, stretched, and reflected. So if you have a function that contains more than one transformation, perform the transformation in the following order. Just like we have order of operations. We have this order for transformations. So we're going to do horizontal translations first, and then if there's any stretching or shrinking, and then reflecting over y or x, or vertical translation up or down. So we're first going to look if the graph is moved to the left, to the right, if it's stretched or shrunk vertically or horizontally, reflected over the x-axis and y-axis, or vertical translation. So let's put them all together. So let's see if you remember from the first part. So f of x plus c, when I add a constant on the outside, the graph is up c units. So that means that a point xy on the parent function becomes x and the y plus c. You moved it up, so the y coordinate moved up. If you moved it down, the y coordinate moved down. If you shifted to the left c unit, so if you added x plus c, it's the x that changed by minus c. And then if you subtracted c from the variable, it moved to the right, so you added c to the x coordinate. Reflection about the y-axis, the point xy, if I reflect by the y-axis, it's the x that changed. The y stayed the same. So it's negative x and y. You can refer to the first part of the lecture if you want. And when I reflected over the x-axis, the x stayed the same. It's the y that changed. And then when the c is multiplied on the outside of the function, regardless if c is greater than 1 or between 0 and 1, the point xy, it was the y values that are multiplied by c. So the point xy transformed into the point cy. And if the constant c was multiplied to the variable itself, not on the outside, then the point xy became x divided by c and y. So this is for horizontal, the x changes horizontally, and this is for vertical shrinking or stretching, the y changes. So what we're going to do next, I have 4 examples next. I'm going to do the last one with you guys in this. I'm going to do the last one, and then as a first written homework assignment, I want you to write down solutions for 1, 2, and 3. And you can do that after you do homework and stuff. So I have my f of x is 1/2 x cubed minus 2. Obviously, the parent function is x cubed. So it says graph the following parent function and the transformed function on the same axis and state their domain and ranges. So what is the parent function? X cubed. So by now you should know how x cubed looks like. So x cubed is that, let's say that this is 1, this is -1, this is 1. So x cubed is going to be that S-shaped graph. So this is x cubed. Now obviously this has 2 things going on. So according to my chart here, if I have more than one transformation, I should consider doing the horizontal first, and then if there is any stretching or reflecting, and then vertical translation. So do I have any horizontal translation? So horizontal translation means to the left, to the right. So do I have anything like this? Does my x have any constant added to it? Well, if I look in here, x is by itself. It's not like x plus 3 cubed or x minus 2 cubed. So it's not that. So I don't have any horizontal translation. So 1, no horizontal translation. 2, do I have any stretching or shrinking? Well, let's look who gives us stretching or shrinking. Stretching or shrinking, vertical or horizontal. We get it when I have that the function is multiplied by c, or the variable is multiplied by c. So my parent function is x cubed. and I do have that 1/2 in front of it. So 1/2 x cubed, yes, I have that the function is multiplied by 1/2. So what kind of stretching or shrinking do we have? Well, the 1/2 is on the outside. It's not like this 1/2 x and everything cubed. So I have this case with my c is 1/3. So c is 1/3. 1/3 is between 0 and 1. So I have vertical shrinking. So yes, vertical shrinking. I can't say that, shrink. With c is 1/2 in this case. So let's see what that happens. According to my charts here, a point xy on your parent function becomes x times cy. So I'm going to write in here that the point xy becomes x comma c times y. So in my case, a point xy is going to become x times x comma c is 1/2, so 1/2 y. So let's follow some points from the parent function. I have the point 0, 0, 1, 1, and -1, -1. So let's see, where is the point 0, 0 gonna stay? We're gonna go. So the point 0, 0 is going to go to 0 and 1/2 times 0, which is 0, 0. So it's just gonna stay there, 0, 0. What about the point 1, 1? The point 1, 1 is going to go to 1 and 1/2 times the y value, 1/2 times 1, which is 1 and 1/2. So the point 1, 1 is going to go to 1 and 1/2, so 1 for x and 1/2 for y. So this point is going to go here. What about the other point, -1, -1? -1, -1 is going to go to -1, -1/2. So then this point, -1, 1 is going to go to -1, -1/2. Okay, so the 0, 0 stays there, and this goes there. So I can draw this if I wanted. This is an intermediate step. So the blue line is 1/2 x squared, x cubed. But that's not what I'm asked to graph. I'm asked to have 1/2 x cubed minus 2. So do I have any reflecting? Is there any negative with the x or outside the x? Is there any negative with the x or outside the x? No, so no reflection. 3, no reflection. What about 4? Is there any vertical translation? Yes, vertical translation happens when you add a c or subtract a c. In our case, we have this -2, so that means that we have a vertical translation down 2 units. So that means that now my point 1, 1 is going to transform into the point 1 and 1 minus 2. I subtract 2 from the y coordinate when I go down. My point 0, 0 is going to transform into, I subtract 2. And my point -1, -1 is going to go, I'm sorry, I should say my point 1 and 1/2, this second one. So 1, 1/2, and this was -1, -1/2. I'm not doing this to the parent function, I'm doing it to the 1/2 x cubed. So 1/2 minus 2 and -1, -1/2 minus 2. So I'm taking this point and move it down 2 units, and then I'm taking this point and move it down 2 units. So the point 1, 1/2 is going to go to the point 1. 1/2 minus 2 is minus 3/2, so minus 1.5. So minus 1, minus 1.5. Or I can just count 1 unit down, 2 units down. So this is 1 minus 3/2. And then the point 0, 0 went to 0 minus 2. So it's going to 1, 2. And then the point negative 1, negative 1/2 is going to go down 2 units. It's going to go here. And this is negative 1 and negative 5/2. So now I can draw. And this is the function that I was interested in to graph. Negative 1/2 x cubed minus 2. So to recap this quickly, when you have a function that has more than one transformation, you have to follow these rules for what transformations to do to the parent function. So you take the parent function and you do any horizontal translation. And then you take that result and you do any shrinking or stretching. And then you reflect that result and then you do vertical translation at the end. So you'll get to practice with 1, 2, and 3. And then if you have any questions, you can ask me. I can make an extra video if you need help with any of these. Just let me know.